All right, everybody. Hello and welcome to our webinar today. We are so excited to have you all here. Today's webinar is going to be Learn Distributed Systems from the Marvel Cinematic Universe. Just a couple of quick housekeeping items. This will be recorded, so you will be able to access it after today's webinar. There are two ways to ask questions or chat. There's the Q&A, and you should also be able to access the chat. So please ask questions, and we will take time at the end of the hour today to answer some of those. All right, I think that was all my housekeeping notes. So I will let Dr. Bilbro take it away.
Hello, everyone. Thank you so much for joining today. I hope that this will be a fun and educational hour. I know that we have people joining us from all over the world, so good morning, good evening, happy midday to you, wherever you hail from. So I wanted to say a little bit about the motivation for this talk. My background is as a data scientist and a data science educator. So I've been doing data science for the last, let's say, 10 years or so. And I've been teaching data science at Georgetown University, for the last 6 or 7 of those years. And one of the kind of most dramatic transitions in my career personally as a data scientist is actually learning more about data storage, which is probably maybe, the least well-represented topic in data science, I think, right now. So there's a lot of coverage about machine learning and data wrangling and hyperparameter tuning and all of these kinds of things. But we don't talk a whole lot about storage in the data science community. But a couple of years ago, when I started getting interested in distributed systems and thinking more about the storage layer, it started to have a huge impact on how I think about what I do and how I think about kind of the right way to do data science. And I'm starting to get excited about sharing these ideas with other people and hearing your feedback and hearing what you think. So if you're a data scientist, and this is a little bit unfamiliar for you, this is like new territory thinking about distributed systems, I hope that you'll feel sort of, welcome, and if you are not a data scientist and you're a data engineer, or a data leader of some kind, and you are kind of getting interested in distributed systems through some other pathway, I hope you'll also feel welcome, and hopefully we can all meet in the middle at the movie theater. So I am a big fan of movies. I go see a lot of movies with my 12-year-old. And we see a lot of Marvel movies. And the last 2 Marvel movies that I saw, the whole time that I was in the theater, all I was thinking is, wow, this is such a great analogy for how distributed systems work. And so I put a challenge out on LinkedIn and I asked you, if I put together a class, would you show up? And I had a lot of people say yes. So this is you calling my bluff and me seeing if I can actually effectively teach some of these kind of core distributed systems concepts in a way that is fun and entertaining. So let's see how it goes. I have 2 disclaimers at the very beginning. So I'm going to show a lot of pictures. There's no code in this talk. This is designed to be very beginner friendly. There's no code, there's no math. I was a math major, but I'm not showing any math here. I'm not going to show any algorithms. We're just going to talk about concepts at a very high level. But I'm going to do that with a lot of freeze frames and stills from different movies. And I don't have the rights to any of them. I don't own them. They're all property of Marvel. And I'm just a humble fan. So if anybody from the Marvel Corporation is watching this, know that I love what you're doing. And please see me as just a humble fan. The second disclaimer is that there's going to be a whole lot of spoilers in this talk. So I sincerely apologize if you have missed one of these movies and I am giving away the ending, but hopefully it'll be worth it because you'll get to learn something. And if you haven't seen it by now, like, you know, that's on you. Okay. So also the other thing I was going to do is I was going to run a challenge and see how many of these movies you guys can identify. So anybody who is like a super hardcore Marvel person, throw it in the chat when you recognize what movie this is from. You know, for each of the slides that I show, if you recognize it, then throw it in the chat and let everybody know that you know which movie this is from, or you can name the character. You know, you can try to do it before I get there. So why am I doing this? I think is a perfectly legitimate question, right? So, you know, as I said, I realized that distributed systems is a concept that not a lot of data scientists are familiar with. And to be honest with you, I don't think a lot of data engineers or really engineers period are familiar with distributed systems as a concept. And, you know, the people who are familiar with distributed systems are people who are working at like the really big companies that have, you know, very big distributed systems that they're in charge of maintaining. But, you know, in general, it's not something that you really learn about unless you go to school to learn distributed systems, which my partner, Dr. Bangfort, you know, he went to school to study distributed systems. So he is, you know, an expert. And so that's one way you can learn, or you can learn by going and getting a job. But there aren't a lot of, you know, boot camps. There aren't a lot of easy ways to learn this kind of stuff. And I feel like that's a gap. And so, you know, the goal here is to kind of democratize distributed systems information a little bit and make it more accessible to everyday folks like us. You know, the other part of this is that one of the big things that I think we have learned from the Marvel Cinematic Universe is that it can be very dangerous to hoard power, right? What is that phrase? Like absolute power corrupts absolutely, right? You know, so having too much power, having too much control, you know, kind of focused in a few small places, like let's say, you know, a few, like let's say 6 or 7 or 8 companies, mostly located in the United States, you know, having them be the only ones who really know how distributed systems work seems like a bad thing. So probably more of us need to know about some of these things to kind of spread out the power a little bit. Okay, so let's get into what is a distributed system. The other thing that I wanted to flag is that whenever you see a blue screen like this, I'm giving you a vocabulary word. So there's going to be, you know, maybe 15 vocabulary words, 10 or 15 vocabulary words that I'm going to talk about in this session. And I'm going to call them out as well as I can so that you can note them down. You know, the goal is to kind of give you as few words as possible to explain as much as possible. But distributed system is an important one. So let's get into what is a distributed system. So a distributed system is a bunch of computers that are working together in a very specific way. And the specific way that they're working together is they're all pretending that they're one computer together. So it's a bunch of, you know, different computers, and they can be all over the world. They could all be in, you know, one region. They could all be, you know, networked in some way, but their job is to essentially pretend that they're just one single thing. So they all have to collaborate and work together in a way that is like not contentious if possible, because the whole premise of whatever application they're supporting is that they are a single thing, you know. And so you can think about something like your bank, right? So when you log into your bank and you ask how much money you have left in your account, if you ask that question and you're in, let's say, Paris, and you look up your bank amount from Paris, and then later you look it up and you're in, let's say, Rio de Janeiro, you should get the same number. You shouldn't get a different number, right? Even though probably, if you really thought about it, you would think, okay, it's probably not really the same server that's serving both of those queries. Realistically, it's probably, there's one server that's in Paris or close to Paris and another server that's close to Rio de Janeiro. And it's probably not the same one that's serving both. But you expect to get the same answer regardless of where you ask the question from. So that's what a distributed system is. It's a bunch of computers working together, so they seem like they're just one. They have a bunch of kind of additional properties that are mentioned here on the slide, but the kind of high level takeaway is, it's a bunch of different servers, but they're pretending to be one thing. So kind of the key part of that is that we need to come up with a way for two of the computers, two of the servers to communicate and work together, right? Because if we can kind of figure out how to get two of them to communicate, you can kind of imagine that we can use whatever they're using to communicate, and we can kind of extend that to some bigger number of servers or computers working together. But here's where things start to get a little bit complicated. So does anybody recognize what we're looking at here? Anybody want to call it out in the chat? Let's see. I don't have any. Oh, Loki Multiverse. Good job. Okay, so season 1 of Loki taught us one very important lesson, I think, which is that very small changes in your timeline can theoretically create complex alternate pathways and alternate timelines and alternate realities. So all of the people that we're looking at, on this slide are Loki, right? These are all versions of Loki that came about from very small, minute changes. So this is the idea, like a butterfly flaps its wings, and all of these kind of changes happen because of that small change. So the butterfly effect has kind of these outsized impacts from very small changes. And in the Loki kind of multiverse, what's important is that it gives us a way to think about each of these different versions as having some kind of autonomy, right? They have some independence, but we also see them work together, and we see them kind of collaborate to do things together during the course of this, the first season of Loki. All right. So how does that happen in the distributed system? Well, we've got, let's say we have two different computers, two different variants. We'll call them variants because we just talked about Loki. So we've got the alpha variant and the Bravo variant. And alpha is blue here and Bravo is orange. And so let's say each of those variants gets a request, at about the same time. So one user tells alpha, to set the key X to the value Y. And, let's say simultaneously, some other user puts in a request to the system and it gets routed to Bravo, right? Because, the two users don't realize that they're interacting with different servers, right? Because it's a distributed system. So there's this sort of illusion that we're just interacting with one thing, but there's actually multiple things under the hood. So a different user comes in and says, well, I want you to set the value at key P to be Q. And those things can happen concurrently, right? Because there's a lot of us around here on Earth and we do things sometimes at the same time. And, the notion of time here is a little bit squiggly. Maybe we'll do another talk on time. Maybe we'll use Back to the Future and time or something like that. But for the purposes of this, we'll say that they're concurrent, which means that they happen, at the same time or so close to the same time that we can't really tell. The first update, the set X to Y, set P to Q, that's actually not a problem because, at least as far as we can tell, there's no real overlap between those two updates. They don't really have anything to do with each other. You know, the key space doesn't overlap. So it's probably not a big deal. But in the lower half of this screen, what happens if two different users try to update the same key at the same time with two different values? How do we decide in our system what we should set that value to, right? So if, you know, the first user tells alpha, I want you to set the key M to the value N, and we tell Bravo through a different user, well, set M to F, how does the system know if they should pick N or F, right? Because somebody's going to be mad, right? One of the users is not going to get what they want. And we also have to make sure that whatever changes we make for alpha, we have to make the, you know, equivalent changes to Bravo, or else we're going to end up with kind of an inconsistent picture, which could lead to you checking your bank account in Paris and you checking your bank account in Rio de Janeiro and getting two different answers, which could be very alarming and could make us lose our confidence in our banking system, which, you know, let's not do that. So this, you know, there's a sort of potential problem here. So I'm going to give you another vocabulary word here. So instead of saying computers or servers, I'm going to call them peers or replicas. And I think that, you know, calling them replica is kind of fun because it gives you that sort of like Blade Runner vibe. And that is, you know, frequently the term that we use in distributed systems. But I think peer is a very good term to describe you know, these the components of the system that are working together, because peer sort of implies this idea of collaboration, right? You're part of a system, you're going to work together. Okay, so let's say we want to keep it simple and we'll have no peers, right? Does anybody know what we're looking at? Let's see, I'm checking the chat to see if anybody can recognize what's on the screen now. All right, no answer. Oh, there we go. Timeline divergence. Very good. Okay, so you know, we're still in like Loki land now. You know, we've got I don't know if you can tell, we've got this sort of like single kind of blue gray thread, and then we've got these sort of little orange tendrils that are coming off of the central line here. And then we've got these red bounds on either side that suggests, you know, if we go beyond the red bounds, then we're beyond kind of a tolerable amount of variance, which does happen in season 1. So, you know, let's say you're thinking, okay, well, if it's really complicated to make everybody agree, to make all of the peers agree, maybe we should just prune them. And who in the Marvel universe is the one who decided that we should prune all of the variants? Pop quiz. I'm checking the chat to see. Kang, very good. So Kang the Conqueror decides, you know, it's too complicated to have all of these different variants. We're just going to prune all of them, and we're going to just have one, you know, one timeline to rule them all, right? Like his timeline. No. So spoiler for the end of Loki season 1. Loki gets pruned. Don't worry, it turns out okay. Probably. I haven't seen season 2 yet, but so he gets pruned. And you know, it's a tragic and terrifying moment in the show because he and one of his variants have just figured out how to work together to solve problems. And just at that moment, when they figure out how to work together, he gets pruned and taken away. And the thing that we realize, okay, we're going to switch out of Lokiverse now into a new universe, or I guess it's still the Marvel Cinematic Universe, but we're in a new movie now. So let's see who can guess which of the movies we're in now. Spider-Man's. So this is one of the more recent Spider-Man movies where currently the reigning Spider-Man is the one in the center. So that's Tom Holland. And so if you haven't been keeping up There's been a lot of Spider-Man through the years, but Tom Holland is the kind of main Spider-Man right now. And the two actors on either side of him played Spider-Man in earlier incarnations. And those earlier incarnations were mostly about the movie industry trying to figure out how to tell these stories. So it wasn't an intentional setup to create this sort of multiverse, but it's a very convenient example to give in a distributed systems tutorial, because one of the things that you realize in this movie, this is one of the first times where, in the Marvel Cinematic Universe, where you get to see a team of, different versions or different variations, work together as peers. And you discover that together they can accomplish a lot more than they can individually. And also the number of them is sort of important. So three peers is kind of the canonical distributed systems example. So, if the canonical machine learning algorithm you learn is logistic regression or something like that, then the canonical distributed systems example is there's three peers, and we have to figure out how to make them work together. And in No Way Home, we get to see the three Spider-Men working together. So the word that we use in distributed systems land for how to describe like what happens when we have peers working together is availability, right? And it makes them stronger because together they can serve more requests, which in the movie, I guess they can fight more bad guys than they can individually fight by themselves. And that's called availability in distributed systems speak. And availability is really important. It would be very frustrating, obviously, and terrifying if you logged into your banking application in Rio de Janeiro and got, a different number than what you got the day before in Paris. But it would be even more frustrating if you logged into your banking application and you couldn't log in at all, right? So if you couldn't log in at all, then you would be pretty mad probably, because you have this sort of assumption that you should always be able to check your bank balance. And if you log into an application and you can't access it, that's a problem of availability. And so you probably see this all the time without having realized it before now. But when you log into an application and it's down, what that means is that either the entire distributed system is down, which is pretty bad, or it's not a distributed system and it is just a single computer serving all of your requests, which is also not great. So now you know kind of what to look for in everyday life. So this is the problem of availability. So let's think about what this looks like from the perspective of a single server that's serving requests. So if it's the banking app, let's say, and we have maybe just a single storage system here that is storing all of the data, all of the interactions that we have with the bank application. It's actually, obviously it's not great because, there's some danger coming. So kind of stay tuned for danger, but it is a very simple problem, right? So if you think about it, let's think about a case where, I'm going to take some money out of my bank account and I'm going to transfer it to your bank account, and then you are going to use that money to buy something. So that order matters, right? So I need to check my account and make sure I have enough. And then I need to do a subsequent action. So the first action is a get, right? I'm going to get my, what's my balance? And so I get a response. And then I'm going to make a decision to move some of my funds into your account. So we're gonna, take money out of my account and put it to your account. So we're gonna change the value of your balance. And then once your balance has been updated, you're gonna make a purchase. You're gonna buy an ice cream cone, let's say. So if any of those things happens in the wrong order, we're going to be in trouble, right? So if you try to buy the ice cream before I've transferred the money, you might not have enough money to buy the ice cream cone. But if we just have a single machine that's serving all of the requests, we don't have to worry about putting things into order. That machine is going to put it into order for us. And so that machine will always be consistent, which is really convenient because the math that gets involved when we have to manually or algorithmically make things consistent starts to get pretty hairy. But at least at this point, things seem simple. And honestly, I think a lot of organizations that are still using a single server, and I actually I can think of a couple right now. I'm not going to name any names because it seems cruel, but there are still a lot of systems that are not distributed, that are actually using a single storage layer. Potentially some of the organizations that you work at, haven't actually set up a distributed system yet. And it might just be because you haven't had enough requests yet for that to be an issue. But at some point, it might be an issue. And a lot of times the problem manifests when something bad happens. So, imagine the Green Goblin comes around and throws, a bolt and takes out our one machine. So that one machine that we used to value for keeping everything consistent and orderly is now unavailable. And because that storage layer is unavailable, we can't do anything, right? So that is extremely disruptive, right? We can't log into our banking app. But it might be even worse than that, because it's possible that there were transactions in progress when the attack happened. And in real life, it's not going to be a Marvel villain that attacks. It's probably just going to be a weather event or, bug or something like that takes the server down. But if the server goes down before it gets to update the storage layer, then there are transactions that might have been in flight that could be lost, which means that, you were at the ATM and you put in the numbers like, give me this much cash. And right after it accepted your transaction, but right before it spit out the money from the ATM, everything crashed. And so you don't have your money, right? It's gone from your account and it's not in your hand because it happened during an in-flight transaction and you're out of luck. So that's not good. And so we need to come up with these strategies for integrating multiple peers so that if one of the servers fails, one of the peers fails, the system doesn't become unavailable, we can still log in. And we can also replicate the data storage on the back end so that we don't lose anybody's money. And that is how you sort of get people to trust your application as your application starts to get bigger and bigger and have to serve more and more people. All right, so who recognizes this slide? Let's see. All right, so this is from Dr. Strange. And what are these kind of mystical looking circles? Does anybody, yeah, the safe houses, that's right. So what are the circles? Does anybody remember what they're called? It's like Sanctum Sanctori or something like that. So here's a question. How many of them are there? Not on the slide. How many of them exist in the Doctor Strange movie? Does anybody remember? I'm looking at the chat. We have a lot of answers. We have infinite, because there are infinite multiverses, which is a very clever answer. Thank you. We've got 13. We've got I don't know. So in the movie, there are three. There are three shown. And I just point out because, 3 is sort of, again, hearkening back to that magic number in distributed systems of having a quorum of 3 peers that form kind of a core of a distributed system. So there's 3. There's actually 4 shown on the screen here, but it's mainly just so you can kind of see the detail Why is it important to have these backups? Why are there backups of the safe houses in Doctor Strange? Why do we need them? Looking at the chat. No answers yet. Maybe somebody's still typing. Okay, so there are multiple safe houses because in the Doctor Strange series, they know that it's possible that one could go down. They know that if one of them gets attacked, there will be a backup. So there's one in New York, there's one in London, and there's one in Beijing, I think. And so the idea is that there are copies because the copies are backups. And if one of them gets attacked, which they do by Dormammu, I think, is the villain in this story. So Dormammu attacks the different safe houses, and there's backups, which keeps the system safe. And that's how it works in distributed systems too. You know, the idea is that we shouldn't be too beholden to any one tier. We should sort of have our confidence placed in the system as a whole, with the knowledge that you know, one of them could go down and the system would still be operational. And that's what we're sort of aiming for in distributed systems. And the word for that in distributed systems land is fault tolerance. So we talk about fault tolerance as the property of being able to theoretically lose one of the peers, or maybe many of the peers if we have more than 3 total, but being able to lose some number of peers and still have the system operational and consistent. So that's fault tolerance. And fault tolerance is really important. You know, in the Marvel Cinematic Universe, something is always going wrong. You know, basically that's the plot of every Marvel movie, right? So, you know, something goes wrong and the heroes have to fix it. And then the movie's over. And then something else goes wrong and the heroes have to fix it. And the movie's over. And that's kind of all of the movies boil down to things are always going wrong. And that's a great metaphor for distributed systems. You know, I think that the sort of unspoken, you know, if the unspoken rule of machine learning is that, you know, a lot of it is just experimentation with hyperparameters and trying different models until you figure out what works, the kind of secret unspoken truth of distributed systems is that something is always broken. And that's just like the natural state of things. You know, when you have a lot of different components, at least one of them is failing. And that's just par for the course, right? It's situation normal. And so, you know, the Marvel Cinematic Universe is a really good metaphor for, you know, why we need to kind of keep our systems fault tolerant. We shouldn't try to create systems that are, you know, immune from failure. Instead, we should acknowledge that failure is going to happen and come up with algorithms and tools and you know, mechanisms to protect the system overall if some parts of it fail. All right, so have I convinced you? Let's see, who knows who we are looking at now? Let's see, I'm checking the chat. Does anybody recognize this guy? Ultron, good job. So this is Ultron from Age of Ultron. So potentially I've convinced you, you're convinced we need peers. We need as many peers as possible, right? So let's build an army, which is what Ultron does, right? He creates a Ultron factory and he produces copies of himself. And then the Avengers have to figure out how to fight this swarm of Ultron drones. So maybe I've convinced you, except, in distributed systems land, we create replicas, right? So this property of making copies, we're going to talk about it as replication, right? So whenever you hear the word replication, I hope you think of Ultron and the Ultron factory. So you want to do replication. That's the goal here. The issue, though, okay, new movie. All right, we'll see who can figure out what movie this is. It's a newer one. Oh, there we go. Quantumania. Good job. So when you have replication, you have the problem that comes with replication, which is that the more replication you have, the more copies you have to coordinate. And in this scene, we have this sort of anthill, and the anthill is a bunch of copies of Ant-Man. They're not exactly copies. They're different versions of Ant-Man who are his variants. But they don't naturally work together, and it actually it takes a while for them to get to the stage of figuring out how to form an anthill from their bodies, so that our hero Ant-Man can climb to the top to try to save the day. It is a lot of work to coordinate across different copies. So you kind of know the bounds now of the problem, right? If we don't have any copies at all, then we're really vulnerable to things going wrong. And we know that things are always going to go wrong because it's a distributed system. And that's just the property. The one true property of distributed systems is that something will go wrong and is always going wrong and probably is currently going wrong, and you just haven't detected it yet. So we don't want to have just one peer because that would be lonely and also not very available and also not very fault tolerant. But the more copies we have, the more peers we have, the more coordination we're going to have to do. So those are kind of the bounds that we have to work inside. So the way that we coordinate between the copies, the way we synchronize, defines how consistent our system is. And this is actually something that is somewhat flexible, right? So you can design a system that is perfectly consistent, that's like strong consistency. And you can design systems that are less consistent, which means that, sometimes, two different versions, Alpha and Bravo, might have slightly different pictures of the world, for some amount of time, but eventually if they have enough time, they'll synchronize. And so you can actually make choices, and you might actually be interested. I would say maybe after the tutorial is over, I would encourage you to Google or to look up what the consistency guarantees are of whatever database you use at work. So if you're using, let's say, Redshift, or if you're using MongoDB, or if you're using Elasticsearch, so I think it would be interesting for you to maybe discover what the consistency guarantees are of the database that you're already using, because it might help you understand some of the other decisions that maybe your organization has made, or some of the decisions maybe your engineers have made about how things are going to work in the application. They might be connected to the consistency guarantees. Also, it's a lot cheaper to be less consistent, right? So if you can deal with having a little less consistency, right? So maybe you're willing to deal with eventual consistency, you can make a much cheaper distributed system. And so that's also one of the big trade-offs, is it's expensive to keep things consistent, and it's maybe not always important. Eventual consistency can be a very popular way to kind of get like cheap consistency. And if you're interested to learn a little bit more about this, I can send you a paper about sort of some of these techniques like anti-entropy, which is a way to, or gossip, which is a way to achieve eventual consistency on the cheap. Let's see, sorry, I got a note. Will we get access to the slides after the workshop? Yes, you will. You will get the slides, you will get a video recording. So you'll have all of this and you don't have to work too hard to take notes. Hopefully you can just enjoy the slides as we go. So you decide, let's say, to keep things eventually consistent, right? So Peter Quill, let's say he says, great, I am Star-Lord. I'm willing to play it fast and loose, and I'm willing to take some risks and cut some corners, and we'll just keep things eventually consistent because that's what I can afford. But as he discovers, there is a cost to eventual consistency, even if it's not maybe your financial cost. And so who are we looking at here? Does anybody recognize this character? This is Gamora. Very good. So Gamora is the love interest of Star-Lord, and everything is kind of going fine until something goes wrong. And one version, okay, spoilers, so cover up your ears if you don't know the ending of this yet. But something goes wrong and Gamora is killed. At least the Gamora from Peter Quill's original timeline gets killed. And so he loses her. But the way that things work in a distributed system is that, losing a peer is usually a temporary state. And what happens is that Gamora comes back, right? So she comes back into the plot. It's not exactly the same Gamora, though. There's something different about her. And does anybody know what's different about the new Gamora that comes back after the first Gamora is killed? Let's see if anybody knows in the chat. That's right. She doesn't love Star-Lord anymore. And she doesn't love him because she is a version of Gamora that hasn't met him yet, that never fell in love with him, right? She's an earlier version in the timeline. So if you sort of picture time as like a stream, she exists on a branch of time where she never met Star-Lord, they never fell in love. And so now she's meeting him and he's expecting her to have all of the memory and the love that she had for him in his timeline, but she doesn't have that history. She missed all of that data, right? And so she's like, who are you again? And she's real mean to him. And it's kind of tragic. And he doesn't take it very well. And so even though eventual consistency can be a cost saver, one of the things that you learn is that a stale read can break your heart, right? So a stale read in distributed system speak is when you ask the system for some information, you do a get, right? What's the value here? And it gives you back an old value, right? So it gives you back some information that's not up to date. And that's what happens here, right? So Gamora is not up to date. She's an old version that doesn't know Peter Quill yet and doesn't love him yet, or doesn't love him, period, and may never love him. So she's a different version. And so a stale read here is where you go and try to do a get, but you get back an old version of the data because the peer that served your request is behind. And in an eventually consistent system, that's allowed. You can have peers that get behind and that are still allowed to respond to the user with old data, with stale data. And sometimes it can break your heart. So how do we avoid that ever happening, right? I never want my heart to be broken. I always want things to be perfectly consistent. I never want to go through what Star-Lord went through. That sounds terrible. So in distributed systems land, the solution is something called consensus. And consensus is a way to guarantee that the peers in the system stay synchronized through every single decision that they make. And it is a lot harder to achieve than eventual consistency because you have to do a lot of coordination. So remember the anthill, the anthill starts to get bigger and bigger and more complicated when you move towards stronger consistency and targeting consensus here. So I'm going to go through at a very high level one example of consensus. This is the kind of canonical example of consensus that you learn about when you learn distributed systems, and it's called Paxos. And if you imagine, we have kind of our magic number 3 peers here, these purple circles. They're working together. They each have this log. So you can see this gray bar next to each of them. That log represents their memory, right? So this is their individual memory. And the goal is that we want them all to have the same memories, right? So we don't want to get into a situation where we have Gamora, who remembers loving Peter Quill, and then another Gamora who's never met Star-Lord before and doesn't love him. We want to make sure that everybody has the same memory. So how are we going to do that? Well, before we decide to remember anything, we're going to talk about it. We're going to try to agree, and we're going to have one peer that's in charge. So that peer that's in charge is going to ask the other 2, do you remember anything from, this part in your log? And if they say, no, I don't remember anything from that part in the log, then the leader will say, okay, well, now let's all remember this. Let's all decide to remember this thing together. And once they all decide to remember it, they all write it to their individual memory, and then everybody has the same shared memory. And every decision they're gonna make in that way. So you can tell, like, it's gonna get a lot more slow, right? So consensus, is probably going to get slower if we let the different machines make decisions independently about what to write to their memory, and then have them synchronize later. That might be faster, but we could end up with a stale read. With Paxos consensus, or with consensus in general, we avoid the possibility of a stale read because everybody is making decisions in lockstep with each other. The other nice thing about consensus is that if one of the machines fails in this quorum of 3, there's still 2 that are operational, and they can still make decisions, and they can still create new memories. And that is a very powerful property, because in the real world of distributed systems, just like in the world of Marvel, we are going to lose our leaders sometimes. And it's going to be hard, and we're going to have to figure out how to recover from losing the leader of our quorum. But we're also going to have to figure out how to bring on new leaders, because new leaders will grow to take the place of some of our older leaders. Does anybody know in the chat who we are looking at right now? Pop quiz. Son of T'Challa, that's right. So this is baby Black Panther, or inchoate Black Panther. So Black Panther dies, but we discover that he has a son who will hopefully rise and kick butt. There is a hitch here, though. There is a problem with zombies. In distributed systems land, a zombie is a leader who's in charge of that, quorum of 3, who's actually not fully functional or not functional anymore. But the other people, the other peers, don't understand yet. So they don't know if the leader is operational or not. And that kind of zombie property actually can cause a lot of problems and really, really slow down consensus. And this is actually one of the reasons why eventual consistency or less strong consistency is so popular, because you can avoid this problem of zombies. And in consensus, you have to figure out how to deal with zombies. But we will get into that in a future thing. One of the big takeaways, I think, from the Marvel universe, and from, in particular from the Endgame kind of saga, is that individually, little groups, little consensus groups are very effective. So if you think about what happened in Endgame, we have all of these individual Marvel groups that independently, in their own individual movies, are able to vanquish the bad guy and solve the problem. But what happens when we try to get all of them to work together to fight against one bad guy? What happens? I'm looking in the chat. Failure. That's right. So things go wrong. When we try to coordinate across a lot of different peers in a very big distributed system, we end up with a lot of new problems that we didn't even know about when we were just looking at 3 trying to coordinate. And so it actually turns out that scaling consensus is really, really hard, just as it is in the Marvel Cinematic Universe. But one cool thing is that if you can figure out how to do it, and that's actually something that we're working on at Rotational Labs, figuring out how to, new algorithms for scaling consensus. If you can figure out how to do it really effectively, it can unlock some really amazing things that you can do. Just as in Endgame, once they figured out how to all actually coordinate together and fight together, they were able to do it. So what can we do if we can figure out how to scale consensus effectively? Well, one thing is we can do disaster recovery. And this is really, really important. So if you ever had your cloud vendor solution go down and kind of lose access to things or have something catastrophic happen, that disaster recovery is really important. If that's never happened to you, I am sorry, because it's going to happen at some point. It's going to be terrible. You're going to have a bad day or a bad week at work. So disaster recovery is really critical so that you don't lose any customer data or lose any of your data. And what that looks like in MCU is that you can actually reverse the snap, right? So Iron Man is able to figure out how to reverse the snap and restore, half of the world that was destroyed. And that's that kind of disaster recovery is possible if you can figure out how to effectively scale your distributed systems consensus. So you can also build self-healing systems. Can anybody think of an example of a self-healing system in the MCU? Just out of curiosity. Everybody says that Morgan is currently the winner of MCU trivia, and he's right again. Groot. So Groot is an example of a self-healing system because Groot can regenerate, right? So this is different from disaster recovery, where we have to undo something bad that happened. This is, a character who can fully regrow limbs, regrow their body, and that kind of self-healing is a very interesting new principle that's kind of coming out of this work. Okay, and then the last thing, so we're almost done. We got like a minute left here, so thanks for hanging in there. The last thing that you can do is time travel, and potentially, some of you are kind of thinking about Kang and where we're going to go next with Kang the Conqueror. I personally was a little underwhelmed with how they dealt with Kang in the most recent Ant-Man movie, and I suspect that they're going to take his story and do some more interesting things. At least I hope so, because I think that this is an extremely interesting character. But one of the things that Kang says is, I don't live in a straight line, and I can skip to the end, and he can also skip to the beginning. And if you figure out how to effectively leverage distributed systems, you too can time travel in this way, which is very helpful for people who are doing machine learning and need to be able to build models that take into account like different moments in time, let's say. So that's all I have for you today. I would be happy to take questions. We've got about 5 minutes left if people want to drop questions in the Q&A. If you don't have any questions, or if you have a question you think will take longer to ask than that, you're welcome to just reach out to me. My email is rebecca@rotational.io. You're welcome to reach out and ask any questions you like, or propose another series, maybe time streams and Back to the Future or something like that. Time travel and Back to the Future might be another fun one we could do. So yeah, tell me what other kinds of things you'd like to learn more about through the lens of movies. And if you want to see a little bit more about what we are working on at Rotational, I would encourage you to check us out online. So you can go to rotational.app, to get early access to our distributed system that we have built that actually allows you to do all of those things: disaster recovery, self-healing, and time travel. So if you want to see that, it's open source. We've got Python and Go SDKs. We're working on a JavaScript SDK. So if you want to check that out, I would encourage you to get kind of early access, free access to Ensign. If you just want to read more about what we're working on, you can go to rotational.io and go to our homepage and read our blog. We have a bunch of blog posts about all kinds of topics, from machine learning to data engineering, and everything in between. And thanks so much for coming to the tutorial today. I hope you enjoyed it. And that's all I've got for you.